The catalog of continuous models opened with the uniform and the Gaussian. Today we add the third leg of the triad, the exponential distribution, the model for weighting. We meet its density and its CDF and put them straight to work on a server, then watch the geometric distribution squeeze into it as coin flips run on a finer and finer clock. Then meet the strange property the limit carries over. An exponential weight never remembers how long you have already waited. And finish by letting that property crack a half-life problem with almost no algebra. Last chapter's bus made waiting uniform. A bus was coming on schedule within 30 minutes. Real arrivals are not so polite. Requests hit a server, parts fail, calls arrive whenever they please. For weights like these, the workhorse model is the exponential distribution. An exponential random variable with parameter lambda has density lambda times e to the minus lambda x for x at least 0. It starts at its highest value and decays, so short weights are always the most likely. Integrate once and the CDF comes out in closed form. The probability that x is at most x equals 1 minus e to the minus lambda x. You may recognize this curve. It made a cameo 3 videos ago as our first continuous CDF. Now it has a name. The parameter lambda is a rate. With lambda 1/2, the density starts low and stretches out. Raise lambda to 1, then to 2, and the curve starts higher and dives faster. More events per unit time means shorter weights. Put it to work. Connection requests at an internet server have exponential inter-arrival times with lambda equal to 1/2. A request just arrived. What is the chance the next one lands within 2 minutes? The CDF at 2 gives it directly 1 minus e to the minus 1 about 0.632. One integral, one answer. Where does this curve come from? From a distribution you already know. Fix a rate lambda and flip a coin on every tick of a clock that ticks n times per second with success probability lambda over n. The number of flips until the first success is geometric. Call it yn. But measure the weight in seconds, not in ticks. Divide by n. The scaled weight xn equals yn over n. Its CDF is a staircase. The probability that xn is at most x is 1 minus lambda over n raised to the floor of nx, a step at every tick of the clock. Now speed up the clock. With n equal to 4, the steps are chunky. At 12, they tighten. At 48, the staircase is nearly smooth. Let n grow without bound, and the familiar limit for takes over. The staircase melts into 1 minus e to the minus lambda x, exactly the exponential CDF. This is the sense in which the exponential is the continuous geometric. Weighting in discrete ticks becomes weighting in continuous time. The same engine that squeezed the binomial into the Poisson runs here a second time. The geometric carried a famous quirk with it through the limit. Suppose you have already waited t seconds. What is the chance you wait at least u seconds more? For an exponential, the answer is the memoryless property, the probability that x exceeds t plus u, given that x exceeds t equals the probability that x exceeds u, the same as if you had just started. The proof takes 2 lines. The conditional probability is a ratio of tails, e to the minus lambda times t plus u over e to the minus lambda t. The factor with t cancels, leaving e to the minus lambda u. Watch what that means. Cut the density at t, keep the tail, and renormalize. The same move we used on the truncated geometric. The rescaled tail lands exactly on the original curve. The process restarts. A used component is as good as new. That is a modeling superpower and a warning label because real parts do wear out. Among continuous distributions, the exponential is the only one with this property. The memoryless property is not just a curiosity. It computes. Hard drives at a server farm have a half-life of 2 years. The probability that a disk survives past year 2 is exactly 1/2. What is the chance a disk needs repair within its first year? We are not told lambda, and we will not need it. Split the 2-year survival at year 1. Surviving 2 years means surviving the first year, then surviving 1 more year, given that first year. By memorylessness, that second factor equals the plain 1-year survival. So the probability of surviving 2 years is the 1-year survival squared. Take the square root. Surviving 1 year has probability 1 over root 2. The chance of failure within the first year is 1 minus 1 over root 2, about 0.293. Lambda never appeared. One last debt to settle. Back when we split the Poisson stream, its bits were drawn with ragged gaps between the dots. That drawing was honest. When arrivals are random in time, the gaps between them are exponential. The key idea of this video, the exponential, is essentially the continuous version of the geometric random variable, memoryless, the model for weighting. Next video opens a whole gallery of densities with the exponential at its root.